Hello, everybody. This is a continuation of week 2 algorithm class. So, in our last class, we discussed different number space, natural number, set of integers, set of rational numbers, real numbers, and complex numbers. We talk about that this complex number has the largest space. Okay, now we move to what is called a power set. Power set. Now, if I have our original set 1 and 2, the possible number of subsets that I can make up from 1 and 2 is what? Set number 1, set 2. I can combine the two sets, and then there is an empty set in every set. So you see that I have 4 sets. So if 4 subsets. So if a set originally has 2 elements, the possible number of subsets of that set is going to be 4. And that is called power set. So if a set A, if A is a set, then the power set of A is defined to be the set of all possible subset of A. So if the number of elements in the set A is 2, is M, then the number of sets or the cardinality of the power set is going to be 2 raised to power M. Now, when we have M to be 2 here, 2 raised to power 2 is going to give you 4. So you can see that the subset for A here is 4. So if A has 3 elements, then the cardinality of the power set of A will be what? 2 raised to power 3, which is what? 8 elements. Okay? Let's have an example again. A is what? 1, 2, 3. That is the original set. Now the power set of A. The power set of A may be written as all these subsets 1, 2, 3. I can have 1 and 2. I can have 1 and 3. I can have 2 and 3. Comma. I can have the set itself. I can have empty sets. And if you count all of it, you have if you count them, you have 1, 2, 3, 4, 5, 6, 7, 8. So if A has 3 elements, then the power set of A, we have 2 raised to power 3, which is 8. 2 raised to power 3 elements, as you can see right there. Okay, so then I move to number basis. You remember computers and number crunchers? You all know that. So the number systems are the technique to represent numbers in the computers. So everything in computer memory has a number equivalent. So computer architecture support the following number system: binary system, which is made up of bits, zeros and ones; octa system, which is made up of what? 0 to 7; 8. Octal system is base 8, right? And we have a decimal system. This is a base 2. Octal is base 8. Decimal is base 10. And decimal system will consist of number from 0 to 9. Up to 9, right? Okay, and hexadecimal consists of numbers from 0 to 9, then from A to F. So generally, base N will consist all numbers from 0 to N minus 1. Okay, so the most popular number bases is what? Hexadecimal and binary. Hexadecimal and binary. So these are the most popular one, hexadecimal and what? Binary for computing systems. As you can see, decimal here is base 10. It's made up of the following digits, 0 to 9. Base 2 is made up of 2 digits. Base 16 is made up of all these digits, 0 to F. And base 8 is made up of 8 digits from 0 to 7. Okay, so the most common bases are what? Binary and hexadecimal, used by computers. And decimal are used by what? People. Okay, look at it again. So if you want to make up base 7 number system, you're going to have 0, 1, 2, 3, 4, 5, 6. 7 will not be included. Okay, and these are the ways you can convert. You can convert from one base to another base. You can convert from one base to another base. That is possible. Okay, so and this is how you do it. For instance, if you are converting from 15, suppose 15 is base 10. Suppose 15 is base 10 number, and you want to convert to binary. So you have to repeatedly divide by 2 because we are going to binary. So you have to keep dividing by 2. 2 divided by 15. 15 divided by 2 is 7. That will give you remainder 1. 2, how many times 2 goes in 7? That will be 3. That will be remainder 1. 2 goes in 3, that will be 1. Remainder 1. How many times 2 goes in 1? That will be 0. Remainder 1. Okay, that is 15. And you read it up from bottom up. So therefore, 15 base 2 is 111. And that 111, if you want to represent it as a full byte, you have to put 4 zeros before it to make it 8. So look at this, for instance. This number is being converted to what? Number 12245. It's now, if I don't write any base here, by default, you have to assume it is what? Base 10. Base 10. Okay. Now, this number is in base 10, 12,345. You want to convert that to binary. So you have to divide this way. You put this number right here, and you put 2 right here. When you divide 2 by this, the remainder is 1. When you divide this by 2, sorry, remainder is 0. When you divide this by 2, remainder is 0, because these are even numbers. Okay, so if you divide that way, if you divide all this through, you'll be having remainder. You'll be keeping track of the remainders here. These are the remainders. Okay, and you have to read it from bottom up. So therefore, after everything, now, one thing I want to be careful with is that if you now, once you have 3 divided by 2, remainder is 1. Then you have 1 here. You just pick the last one, you just put it right there. Because 2 cannot go in 1. So you just put this as the remainder. And you have to read from bottom up, and that will be this number. And you can also convert this number back to what? The decimal equivalent. back to the decimal equivalent. Okay, it is possible. Once again, you can convert from one number base to another base. If you have number 1, 2, 3, 4, 5, if I give you this number, I don't state the base. You have to challenge me, or you assume the base 10. So base 10 is called denary. Denary, then that's used by human. How do you convert that to binary? How do you convert this to binary? Binary means base 2. You have to keep dividing that number by 2 and keep track of the remainder that right there. Okay. Now, octa, you can convert decimal to octa. You have this decimal number 1, 2, 3, 4, 5 in base 10. So if you want to convert it to octa, which is base 8, you also have to divide it by 8. When it was base 2 binary, convert it to binary, I have to divide by 2. But now I am converting decimal to octa, I have to divide by 8. So, and if you divide that number by 8, you keep track of the remainder, and you have to read from bottom up. At the end, you see that the last one here, 8, how many times 8 goes in 24 is 3 times. The remainder is 0, right? So when you have the remainder less than 8, you just put it right there. So 1, 2, 3, 4, 5 in hexadecimal, decimal number is the same thing as what? 30071 in octa. Can you see that? So that's how to do it. So it's super easy. I'll do it once again. Look at it. 2 divides this to give this. Remainder is 1. When you divide this by 2, remainder is 0. You are going to get this. 2 divided by this gives you this. Remainder is 0. This divided by 2 gives you this. Remainder is 0. This divided by 2 gives you this. Remainder is 1. This divided by 2 gives you this. Remainder is 1. You keep going on and like that. Okay, and you can also convert an hexadecimal to, a decimal number to hexadecimal. See, we picked the same number here, 1, 2, 3, 4, 5. We converted to binary. We also converted this number to octa. You can also convert it to what? To hexadecimal by dividing. So you have to divide by 16 because 16 is hexadecimal notation. So you divide this number by 16, it's going to give you this, but the remainder is 9. When you divide 771 by 16, it's going to give you 48, but the remainder is 3. When you divide 48 by 16, it's going to give you 3, but the remainder is 0. When you divide 3 by 16, when you divide 3 by 8, it is impossible. Just pick because this is smaller. The 3 is smaller than 8. Just assume your remainder is that 3. Then you read from bottom up so that you have 1, 2, 3, 4, 5 base 10 is what? 3039 in base 16. Okay, that's how to do that. So let's have another example. You have another number here, 725. See that you have to specify the base, because this 725 can be a base 10 number, by base 8 number, it can be a base 9, it can be base 10, it can be base 16. So you have to make sure you specify the base. Okay, so now when you want to convert 725, which is denary, to base 16, you divide that number 725 by 16, that will give you 45, and the remainder The remainder, let me just use that. So 725 by 16. The remainder is going to be 5. But 16 goes in 725 45 times. Then 16 goes in 45 times 2. The remainder is 13. Now, in 13 is hexadecimal is represented as D. So 16, so 13 and D means the same thing, okay? Now, if you divide 16 2 by 16, so 16 is bigger than 2, you just use this, your remainder is the smaller number, 2. And you read bottom up. So you don't say 2, 13, 5. Because this 13 is D, so you just say 2D5. Just an hexadecimal. Okay? And you can convert from binary back to hexadecimal, back to decimal. That is very straightforward. So if you have 1, 1, how many zeros? 1, 2, 3, 4, 5, 6, 1, 1, 1, 0. This is base 2. That's a very big number. Now, all you have to do, you see, now you can start putting index on top of this number, starting from the right. Must start from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All the time, if you are converting binary to decimal, you have to write out the binary numbers. Then from the rightmost side here, start putting index on top of them, or which is, we can call it the power index, power index. From 0, you have to start from 0 down to the last one, which is 13. So this one is 13. Now, all the one with zeros, you can neglect them because they will give you zeros, by the way. All this one, you will neglect them. You just, now, remember the power of this is 13. You just pick one, this face value, 1 times the base raised to power 13. Each of the number times the base raised to power. That's 1. There's another one here, 1 times 2 raised to power 12. That is why you have this. So all this one will be 0. Again, you have 1 here. Okay, this will be 1. See the way I'm picking it? So plus 1 times 2 raised to power 5 plus 1 times 2 raised to power 4 plus 1 times 2 raised to power 2. I will neglect this. Then the last one is 1 times the power is 0, 2 raised to power 0. That's what you have here. And that will give you back your number. That will give you back the number. Let me have another example for you. I like multiple examples. I think the first is not clear. Most likely you get the second. Suppose you are converting this number. This binary number to decimal. Suppose convert that binary. That number could be a decimal number. It could mean 1 million. No, it could mean 1 billion. 1,101,110. But if I put the base there, that is not a decimal anymore. But I want to convert this binary to decimal. Now, I told you, you write out the number, you put index like a position on top of them from 0, 1, 2, 3, 4, 5, 6. You have to start from here, like that. Now, all the one with zeros, you neglect them. You don't need them. So now, this is base 2. I'll now say 1 times, that's 1 times 2 raised to power 6. Each of the number times the base then to the power, plus this number 1 times the base, this power 5. That's how you do it. Okay. And if you are converting octa number to decimal, look at it again. Octa to decimal, you multiply. You see, when you are converting any number to any base, you divide. But if you are going back to decimal, you have to multiply. So this number now, 30071 base 8. You are going to what? Decimal. When you convert to decimal, you have to start putting powers and index on top of them. So from 0, 1, 2, 3, 4. Right? I will not pick each of them. I will pick 3 times the base raised to the power 4. I will not use this because if I use 0, the 0 will give me 0. So I would neglect anything with zeros. And I will put 7 plus 7 times 8 raised to the power 1. See, 7. Each of them times the base is power the power plus 1 times 8 raised to the power 0. That is exactly what is here, and you will get what? You will get back 1, 2, 3, 4, 5. Okay, so that is very interesting. And in C++, you can represent different number bases. But I told you the most popular ones are what? Binary, octal, decimal, and hexadecimal. So this is base 2. You use 0 and 1 to represent it. Base 8, you use 0 to 7. Base 10, 0 to 9. This is that. Now, an example is this of each of them. How do you represent them in a C++ language? So you can use this. Look at this prefix, int val. When C++ sees this, it recognizes val variable as binary. Okay, and for octa, all you have to do is to put this 0 before it. And C++ will recognize that as octa. But integer is straightforward. And of course, you know that by now that hexadecimal is what? OXFO. If you print out sound, if you fix that with a number, that will give you a memory address of that number, which is always in hexadecimal. It's always in hexadecimal. Okay. And you have what is called ASCII code. You have talked about that before. It is called American Standard Code for Information Interchange. And that uses what? 8 bits coding system to represent 128 characters. Okay, uppercase A is coded as number 65. Character A is coded as 65 decimal, and then it is represented as 65 in base 2. Internally, we use bits to represent any data. But ASCII code uses what? Integer number, decimal number to code every characters. But in the memory, they are eventually converted to binary. Okay, so this is ASCII code. Once again, ASCII is what? American Standard Code for Information Interchange. 8 bits. Then for representation, and that represents 128 characters. We also have extended binary code, something like that. Those some stores. So these are all you have. Look at them. Look at them. So take notes. The ASCII code for lowercase equals uppercase plus 32. Look at this formula. So uppercase A, the ASCII code is 65. So lowercase a is going to be 65 plus 32, which is 97. So lowercase is coded as what? 97 in computer, in ASCII code, but internally, lowercase is coded as 97 to base 2. Okay. And the following C++ program, we print all the ASCII values. Look at it, it's very simple. You know, all you have to do is so you start from ASCII code representation, I equals 32, I plus plus. I just want to print a few ones, okay? And now this expression is to print. Now, if you do that char, if you do this char, that will start from that. You know, there are a lot of them, so we can't print all of them. Let me see. 1, 2, 3, 4, 5, 6, 16. Yeah, that's 128. That's right. That's how to print all of it there. Now, this line is to print 16 characters per line. Okay. Now that will give you this. That's fun. So all these are what ASCII. But we have more than this. So therefore, there is Unicode and there is extended one. Okay, that's extended one. Okay, so look at how we are mixing math with coding. It's so interesting. You know, computing is very interesting. It's very interesting. It's very interesting. So once again, look at it. Look at it. You have your preprocessor library directives. So you have your using namespace std. You don't want to do std all the time. Okay, and this is an end line, not really compulsory. This is a output prompt. I mean, it's telling you what you want to do. ASCII code representation. Now, to print all of them, you have to start from here. For char I equals, remember char is integral keyword. Char I equals 32, I less than 127, I plus plus. Now, CRI. Now, this will give you this. Normally, I'm not using int. If I say int now, I'll be printing only the numbers. But if you put char right there, it's going to give you the exact characters. Okay, and then this modulo operator is to print 16 characters per line. And that will give you this. That will give you that. Okay. Then we move to matrices. Matrices is a rectangular array of numbers in rows and columns. Okay. The first I here is for row. This is for column. Okay. So we have 418295. This has got 2 row 1. This is the first row. This is the second row. This has got 3 columns, column 1, column 2, column 3. So the dimension of this matrix is what? 2 by 3. It has to be all the time row by column. Take note of that. Row by column. And you can find the transpose of the matrix. Transpose of the matrix. Also, we talk about exponent. You must have done this in pre-calculus and calculus. So loss of exponents. If you have 2 raised power 3 times 2 raised power 5, that will eventually be 2 raised power 3 plus 5, 2 raised power 8. If you have 2 raised power 3 raised power 5, it's not the same thing as this. So all you have to do is when you have 2 to power to another power, you have to multiply the 2 powers. I'll give you 2 raised power 15. See, they're not same. Okay. And if you have if you have an expression of this form, 2 raised to the power of 5 divided by 2 raised to the power of 2, that will simply give you 2 raised to the power of 5 minus 2. Let me put 3 here. 2 raised to the power of 5 minus 3, which is 2 raised to the power of 2, which is 4. Okay, take note of that. Any number raised to the power of 0 will give you 1. And when you have x to the power negative n is the same thing as 1 over x to the power n. Okay, and then we have the rules of logarithm, which is very, very important. Logarithm is very, very important. So if I raise 10 to the power 2 to get 100, then the log of 100 equals to 2. If I raise 10 to the power m to get 1000, suppose if I raise 10 to the power m to get a, then the log of a is the power. 10 is the base. So the logarithm of a number with respect to the base, the logarithm of the number with respect to the base. Now, your base can never be equal to 1. Okay? The log of a number x base b, suppose that log is, let's call it y. Then the base raised to power y will give you the number. Let me use another notation for that. Let me use another notation for that so I can get it easily. Now, if I say log, let's say top base equals right hand side, then base raised to power right hand side will give you top. Now, if you can memorize this, it's going to help you. Log top to base equals right hand side. Log top base equals right hand side. Then base raised to power right hand side gives you top. Look at it. Log 4 base. Now, I am not writing log 2 raised to power 4. This is not the same thing, okay? Log 2 raised to power 4 means log 16. That's not what I'm doing. Okay, so be careful. So if I have log top, which is 4 base 3 equals y, then the base raised to power y will give me 4. So this is a way of converting exponential expression to logarithm. Now, why do we need logarithm expression? Logarithm expression is a way to scale down a number when you're representing it. Okay? For instance, log of 100 equals to 2. Because if I raise 10 to the power 2, I get 100. Log of 1 million will give you 6. So on a log scale, 1 million is represented as what? Number 6. So you see that logarithm is useful for scaling down numbers to make sure big numbers are represented as a small number. But you have to put as a legend log scale on your graph. So if I'm on a graph now, if I'm on log scale graph, and I have 1 here, 2 here, 3 here, 4 here for my data, right? You know that this one is going to be 10. This is equivalent to what? 10. This number 2 is equivalent to 100 because 10 to the power 2 is 100. And this number 3 is equivalent to 1000. Okay? So that is what log does. Okay? And this is an example. There are a lot of examples, right? Now, there are rules of logarithm, sorry. Rules of logarithm. So when you have log of AB product, will be log of A plus log of B. When you have log of division, it will be log of A minus log of B. When you have log of A to power M, it will give you M log A. Note that log of A base B is actually can be represented as log of A divided by log of B. And note that log of B, A base B is never the same thing as what? Log of B to power A. It's not the same. So be careful with that. Be careful with that. So, I think we'll come back to a lot of this. Sorry about that. Yeah. Analysis of algorithm. Okay. That's okay. Now, if you want to solve something like this, these are just these are pre-calculus 1 and 2, okay? Now remember, we are trying to look for in all these expressions, these are question on logarithm. We are trying to look for the value of x in each of them. For instance, 4 to power x minus 2 equals 3 x plus 4. Right now, this is the base. This is the base. Now, different bases, you have to introduce log. So you have to log both sides. Log or ln 4 to power x minus 2 plus log 3 to power x plus 4. Then you put this at the back. X minus 2 log 4 equals x plus 4 log 3. You multiply everything. So x log 4 minus 2 log 4 equals x log 3 plus 4 log 3. And then you rearrange for x. You'll be getting x into log 4 minus log 3 equals 4 log 3 plus 2 log 4. Then x will be what? 4 log 3 plus 2 log 4 divided by log 4 minus log 3. And all this is a number, it's an expression. Okay? Another one is here. 6 to power x plus 3 equals 4 to power x. So they have different bases. So introduce log, and the power is a variable. When you have different bases and the powers are variables, then just log both sides. You can ln it. So you can log 6x to power 6x x plus 3 equals log 4x. Okay, now bring the power right here, x plus 3 log 6 equals x log 4. You do the same thing. Okay, you do the same thing. Now, let me tell you something cool about logarithm. Log of, be careful, I'm going to solve more in class. Log of a number must be to a base. The base can never be 1. In a logarithm system, base can never be 1. It must be any number greater than 1. Okay, it might be 1.1. Okay, it might be 1.01. But your base can never be what? 0. Because you know why? The reason is this. Let me tell you the reason. log of A to base B. Remember, once again, it's not the same thing as this, so you have to be careful. This is just B to power A. But if I'm saying log of A to base B, it actually means log of A divided by log of B. Now, log of 1 is 0. By definition, log of 1 is 0. Because when I raise 10 to power 0, I'll get 1. So if I do this, I'll have log of A over log of 1. So log of 1 is 0. You cannot divide by 0. So your base can never be 0, okay? For logarithm. I think I will stop here for today. And I hope this is very informative. Thank you very much.